Hello everyone, this is Spencer Snowling from Hydromantis, and I'd like to welcome you to today's webinar. We are going to be talking about the model developer tool that is part of your GPSX package and is designed to help you edit the biological models that make up the activated sludge portion of GPSX. And it's one of the more advanced tools. It's certainly one of the more powerful ones. And let's hop into today's webinar. My name is Spencer Snowling. I'm Vice President of Product Development here at Hydromantis. And as one of the main developers of GPSX over the past 15 years or so, I use Model Developer on a frequent basis. It is the tool that we use to create the biological models that we put into our software. And so the tool that you see in GPSX right now is essentially the same thing that we use to do all of our regular model development. So this is something that we make available for you to be able to use if you need to be able to customize the models for your own use. So I'll just have one quick word here. As per usual, if you have any questions as we're going along in today's webinar, you can type them into the GoToWebinar dashboard. There's a panel there called questions. Usually what we do is I'll just let those collect as we're moving along, and then I'll stick around at the end of the webinar to answer questions for 5 or 10 minutes. So I'll start out with the ones that I see that have been typed into the questions box as we move along. Okay, so here's the plan for today. I'm going to talk a little bit about dynamic mechanistic models, and I'm going to use ASM1 as the example for the work that I'm going to demonstrate here today. It's, as you probably know, the very simplest, the very first activated sludge model that was published, and I'm going to stick with the simple one to talk about customization today, just to keep all of my examples very straightforward and clear. Talking about how the models are put together, the way that we have state variables and we do mass balance and so on, sort of sets the context for how Model Developer is a useful tool. Now, Model Developer is essentially a tool that allows you to use a big matrix of information. So I'm going to talk a little bit about the model matrix notation that is come out of the original ASM1 publication. And I'm going to talk about typical things that you might do with the Model Developer tool in GPSX in terms of being able to modify the existing models that are there, being able to do various types of interesting things with them, typical applications that we might have. And I'm going to run a couple of, I'm going to obviously show you how to navigate your way through the Model Developer tool. And then I'm going to have a couple of examples where I will generate a couple new models and then put them into GPSX and then use them in various different ways. And as always, I'll be able to answer any questions that you have when we get to the end of the webinar. Okay, so this is a little bit of review for those who may already know about how the ASM type models work. Now, just a little bit of terminology off the top here. Today's webinar and Model Developer as a tool deals with changing the fundamental equations of the activated sludge model. So the growth equations, the death equations, hydrolysis, and so on. These are really the equations that describe the biological part of the model, and it's essentially the same equations that are used in all of the different objects that you find in GPSX. So for the most part, they're the objects that are colored like activated sludge, the brown ones. The completely mixed tank, the plug flow tank, oxidation ditch, SBRs, MBRs, and so on. So all of those types of unit processes use the same biological model. So for today, when I talk about model, I'm really specifically referring to the set of equations that describes the biological activity. So all the dynamic activated sludge models that we use in our industry are all based on a similar underlying structure. They're all based around the ideas that were developed originally in the ASM1 model from IWA that was published, well, pretty much 30 years ago now. So the ASM model introduced that very first set of state variables, those components around which we do mass balance to be able to describe growth and death and the transformations that go on in the typical activated sludge process. And as you probably already know, these state variables are various forms of COD. We have the substrate forms of the COD, we have the biomass forms of the COD, there's inert forms, there's readily biodegradable substrate, and so on. We also have state variables for the various forms of nitrogen, ammonia, nitrite, nitrate, and so on, and same thing for phosphorus. And the more advanced models, as we got sort of later in time, as things developed on, they also have state variables for other things too, micronutrients, for the various components that are used to make up pH calculations and other things. So I'm not going to deal with any of that sort of later on development stuff. I'm just going to stick to talking about COD and nitrogen for the most part today. So the actual equations that are in the models, the ones that describe how things change, how things are transformed from one particular unit of COD to another one, those describe two things, the actual model equations. One of them is the kinetic part, the how quickly things are transformed from one to another. How fast does the biomass grow? And so that tells us something with respect to time, and that's the part that controls the prediction of the effluent quality based on things like tank size and SRT and so on. The other part that's there is the stoichiometric part. How much of each thing is used up when you produce another thing? So for example, when I grow one new unit of COD of biomass, how much substrate was required, how much oxygen was required if you're growing it aerobically, and how much nutrients were required and various other things. It's sort of those stoichiometric ratios. For every unit of substrate that I remove, how much new unit of biomass do I get? So many of these transformation processes are occurring simultaneously. So in the ASM1 model, there's actually 8 rates going on, 8 processes going on. There's a couple of different kinds of growth of the heterotrophs, there's growth of autotrophs, there's hydrolysis, there's transformation of the organic nitrogen and so on. These are all happening simultaneously in your big completely mixed reactor. And each one of those is adding to or subtracting from the various components. And we solve all of those equations simultaneously to be able to get an accurate prediction of the concentrations. So, as you may know, ASM1 actually has 13 state variables in it. Now, I'll just mention for those who are already familiar with ASM1, I know that XII, the particulate inert inorganics, is actually not part of the original version of the model, but it is part of the version that we have in GPSX. But for the most part, we have a number of units of state variables that are based on COD, and those are your substrate, your inert COD, and your biomass. And then we have some ones that are here for the various forms of nitrogen. And those are the ones that we do mass balance around using a big matrix of information, do the mass balance on in order to create the activated sludge model itself. So these are the versions that are there for the ASM1 states, for the ASM1 model. Now, as we go to the more advanced models, as we went further in time, when we get to ASM2D, which allows us to do BioP modeling, there were more state variables. There was the BioP bugs, there was the more advanced fractionation of the substrate, and so on. So what the model matrix notation does is it allows us to keep track of all of that complex information in a nice sort of concise way. It's a way to allow us to have a matrix that shows all of the mass balances and all of the derivatives all in one place, and keeping track of everything that's in that particular model and how it affects each one of the state variables. So this kind of idea of publishing a series of equations as a sort of a matrix was not completely entirely new, but it was sort of developed up within our wastewater industry, really in that first ASM1 report when that first model was published. So it isn't, of course, now the standard way to publish a new model. If you're going to do that, you'll see them published, maybe not necessarily the entire matrix in its completeness, but usually some chunks of that matrix will be displayed in the publications that you might find for new models. So this is the basis for the model developer tool that we have. We want to show that entire matrix for the biological model that you want to be able to edit and make changes to. And it's sort of designed to work a little bit like a spreadsheet where you can go in and find the particular row and column for the stoichiometric relationship that you want and make the change appropriately. So I'm going to do a little quick description here of how these model matrices work, and then we'll jump into how that looks when we see the same information in the software. So model matrices are basically an arrangement of information that allows you to understand how models are put together. Models could be just simply a big pile of equations that we publish, but when they're put in this kind of format, it's much easier to understand actually how things fit together and how we can control the mass balance and make sure that everything makes sense. So usually these model matrices are made up of columns of one for each one of the state variables that you will find in your model. So I got 3 sort of generic state variables showing here. And then we have a number of processes that are going to be going on simultaneously in this particular reaction. And we can have as many state variables as we want and as many processes as we want. And then we can use the information within the matrix to describe how those processes affect these state variables. So this portion of the matrix is where that stoichiometry is contained. So for when rate 1 is going ahead and when we have 1 unit of new information, 1 unit of growth happening, the information in this particular part of the matrix will describe how much of state variable A is going to be used up and how much of state variable C will be produced and so on. On this side of the matrix is where you find all of the kinetic rate information. This tells us how fast things are going to happen, and this is where you find your first order relationships or your second order relationships and your Minode terms and so on. So often you will find in matrices like this that they'll be filled somewhat sparsely with information like this here. This showing that, for example, when rate 1 happens, we're producing some new amount of state variable A, but we're using up some amount of state variable C here. And we can find that you can do all of these in various combinations, and sometimes it's not a strictly one-to-one relationship. You may find that there is other stoichiometry that we are calculating on the go here. These are parameters that can be adjusted. Sometimes they don't always necessarily mass balance. In the models that we do in the wastewater industry, they do, but that isn't necessarily a function of model matrices by themselves. And then over here on the right-hand side, you'll see various forms of equations. They could be just constants or they could be first-order relationships. And usually they're, in the wastewater models, quite complex, lots of terms in these equations. And those are contained over here. They may or may not contain the state variables that are being described here. Usually there's going to be at least some connection in that relationship. The nice part about it is once you've got that filled out and you've got all of that information stored there, you can see that we can look at the mass balance by going across each row here. So for example, we can see that this particular rate actually mass balances because for presumably all of these state variables are in the same units. For every unit of state variable A that is being grown, we are consuming 1 unit of state variable C. So if you see this in the ASM1 model, you can keep track of COD going across. If you add it up going all the way across, you will find that it adds up to 0 because it mass balances the COD for each one of those rows in the matrix. The nice thing too is that if you go down a column here, you can see that it's the way that we actually write the derivative. So the derivative for state variable C here is taking the stoichiometric relationship, multiplying by the rate at which it is happening, and then doing that, summing that up all the way down the length of that column. So for example here, -1 times Ka, -1 times C, that is actually the value of the derivative. That's telling us how fast state variable C is being consumed in this little generic model that I'm presenting here. Okay, so that's a very simple sort of generic explanation. This is the actual ASM1 model matrix as it was printed. I scanned this sort of right out of the old ASM1 report. It's a little bit ugly to read here due to the font size, so I'm going to zoom in on just a couple of individual parts here. This is the stoichiometric part, and we can see all of the various state variables across the top here. SI, soluble inert material, soluble substrate, and there's some biomass here, and the various forms of nitrogen are sort of down here at the end, and this is alkalinity down here on the end as well. So those are there, and we have the relationships that tells us when we grow for this particular rate here, the very first rate is the aerobic growth of heterotrophs. That is going to consume some substrate. It is going to produce some new biomass. It is going to consume some oxygen, and it is also going to consume a little bit of nitrogen here as a nutrient for growth and consume a little bit of alkalinity too. So that's telling us our stoichiometric information. And if we move over to the right, we can see here the actual process rate. This is a first order relationship, the growth rate times the amount of biomass. And then we have our saturation terms, which we use to control when to apply these equations for various environmental conditions, whether we have oxygen and whether we have nitrate, and that allows us to distinguish between, anaerobic conditions and anoxic or anaerobic conditions as well. So So these types of equations are the ones that are available for you to be able to adjust or make changes to with the model developer tool. You can change the stoichiometric relationships, you can change what's in these equations, and then generate your own new version of the model. So just to summarize that, I got one slide ahead of myself here. The model developer tool allows you to basically create new biological models by editing that matrix of information. You can start from one of the existing models that we have, like ASM1 or 2D or New General or so on, and then you can make changes by adding new things to that model or deleting the ones that are there, or basically starting from scratch if you like. You can add new rates, and by that I mean you can add new rows to the matrix, or you can get some of the other state variables involved. We have some extra ones that we've developed for you to, if you want to use up some brand new ones. And that's adding new columns to the matrix. So you can generate new rate equations, you can generate and get some new state variables involved, and you can also change the kinetic equations or the stoichiometric relationship. So you could, for example, add a new row that would be the growth on a new different kind of substrate. You could add a new column to represent that substrate itself, and then put in a new different growth rate and so on. You can also change the default values of all the various parameters. This is something you can actually do outside of the model developer tool. But if you're making a brand new model, you will take the time to develop all the default values that you want for the various kinetic parameters, and therefore you can set what you want those default values to be, and that will be the same across all of the different unit processes. So, as I mentioned, these can be done. Typical uses that we would see is to add new biomass types or new substrate types into the biological reactions. We can also use Model Developer to modify the growth equations so that the growth is inhibited in the presence of other, say, potentially toxic substances. Or you can do other types of transformation processes that are in addition to the ones that we have. If there's some other type of conversion of the COD or some other thing that's doing something to remove or modify the nitrogen or phosphorus or something, you can add that in by adding in some new rows. So let's get on to actually talking about the tool now. So Model Developer has actually been part of GPSX almost from the very beginning, because as I mentioned, it is the tool from which we actually develop the models in GPSX. So it has been available to the public as part of the GPSX package since long before my time at Hydromantis, actually. I traced it back as far as I could tell, at least 18 years, probably 20 years we've had the Model Developer tool, since at least version 2 of GPSX. Originally it was an external tool. It was an Excel spreadsheet-based tool that had a lot of other code built around it, and it shipped with all the copies of GPSX, and it was available with all of the licenses. And users could generate new models for a limited number of unit process objects. In the beginning, it was only for the CSTRs and the plug flow tanks, and I believe the SBRs. And this is what it looked like back in the day. You had a lot of information that was contained in this matrix with all the state variables across the top and the rates down the side, and you could type out what you wanted your equations to look like, and it was all done within an Excel spreadsheet. And then you would hit the generate button and it would produce some code. So 5 years ago, when we produced the new modern version of GPSX, version 6.0 at that time, we reinvented the Model Developer tool as a new tool within GPSX. So it's now a new, fresh interface design. We got rid of the Microsoft Excel part of it, and it's now launched from within GPSX. There's a much better organization of information. If there's one thing that the Model Developer has to do, is it has to store and present and allow you to edit a very large amount of information. There's a lot of equations, there's a lot of parameters, there's a lot of naming of variables and other things that have to be there. So we've tried to sort of use a tabular format where we keep things sort of organized in a way that makes some sense and allow you to browse back and forth between different parts of the model easily. We then also have, and this is brand new, excuse me, model validation tools. So once you've put together your matrix, you can look for parts of that model which might be missing or conflicted, or whether you have duplicate variable names. That's something that's quite easy to do when you have a large model, to make sure that you are not missing any parts to your model, that you can't actually generate code that doesn't make any sense. And then we've expanded it to as many of the unit processes as we can. So it's not quite 100% of all of the ones that are available in GPSX, but very close to it. All of the different types of things that you would find in the suspended growth section and in the attached growth section of GPSX. So you start Model Developer, you get access to it by going to the Tools menu and clicking on Model Developer, and it will pop up a new window that looks like this. And what the first thing you'll see is actually a listing of the particular library that you are working in. So a library is basically the collection of state variables in which you can write your model. And we have lots of different options available for those, and then you can move on to some of these other tabs that describe all of the different parts of that model, including the definition of all the default parameters. So rather than doing that in the slides here, I'm just going to hop straight over to GPSX and show it to you live here. So this is GPSX version 6.4, and if I go to the Tools menu and I start Model Developer, oops, it opened it up on my other monitor. There we go. This is what it looks like, and just to give you a little quick tour here, if we go to these different various libraries that are available, so I'm going to select these names here are explained in the GPSX library selection menu. This is the carbon nitrogen library, CNlib. We can see that we have all of those state variables like the ones that I described earlier for the ASM1 model. And these are the ones that are available for you to do mass balance around. These set of state variables are the ones that you can use in your matrix. And if we go to the matrix itself, we can see that kind of relationship that we had written earlier. So it shows the state variables across the top, and it shows the various processes down the side. Now this is ASM1. It's got 13 state variables and 8 rates. So you can, as I mentioned, start to adjust this and make changes to this model. And so let's do that as an example here. What I'm going to do is an example where we are going to add a new row to this matrix and then create a new rate that is going to do a biodegradation of inert particulate COD. Right now, if we look at the inert particulate COD state variable, we'll see here in the very simplest models that we have, ASM1 is the simplest model that we have, there actually is no process that actually does anything to XI, the particulate inert material. It kind of comes into your system, floats around, gets collected up and accumulated as part of the mixed liquor, and then it goes out in the sludge. So that may or may not be a perfectly realistic explanation of that type of COD. So let's say, for just argument's sake, we want to modify this biological model so that there is actually a little bit of degradation of that when you have very long SRTs. We've actually implemented this into our Mantis 2 model. So the first thing that I want to do is add a new row down here. So I'm going to right-click. I'm going to add a row. And actually, I'm going to put this on the bottom. You can actually drag these around. I'm going to drag that up here. So put it on the bottom, and I'm going to say this is degradation of inert COD. And this is going to be a rate that is going to change the COD state variable. So that means that the units here should be grams of COD per meter cubed per day, because this is a rate that changes that state variable, so it has to be the units of the state variable per time. Units of the state variable are units of COD per meter cubed. And then now I need to specify how that new rate is going to be implemented in this model. So as I mentioned, what we want is something that is going to remove a unit of XI and then produce a unit of XS. XS is the particulate slowly biodegradable substrate. So we're going to, at a very slow rate, remove some of that stuff that's completely inert and actually do a little bit of biodegradation on it to get it into that slowly biodegradable format. Okay, so now we've got another new row here. And we're going to say, I'm going to leave all the rest of this blank because it's not going to affect any of these other state variables. Okay, so now we need to move on to the next step, which is to look at the actual kinetic equation that is going to describe how fast this happens and under which circumstance this happens. So here's our new rate. This is still blank because we haven't entered anything yet. So let's say that for argument's sake, we're going to make this a first order rate. It is going to be some constant times the amount of XI that we have in our system. So I'm going to make up a constant name here called kdeg times XI. So that's a simple first order relationship, and we can see that that's now been accepted here as part of this particular system, and we're going to have to define what that degradation constant value is. So this would be a good point to actually highlight that model validation step. If I go to File and go to Validate Model, it's popped up this window which says we still have one issue. This isn't a complete model yet. What the issue is saying that we have this one parameter that's not been defined anywhere yet. So that's because we have to go over here to the model parameters page, and we have to add it to the list of parameters. So what it does is it double checks all of the equations to make sure that they have all of the terms in that equation have been defined in some way or another. So what I'm going to do is I am going to just add on a new header down here at the bottom. And I apologize, it keeps popping up on my other screen here. Okay, so I'm going to make a new degradation of inerts section here. And I'm also going to add a new row, and this gives me the opportunity to add a new parameter here. So kdeg, whoops, that's the parameter that I made up before. I got to give it a name here, so we'll call this the inert degradation rate constant. You can type pretty much whatever you like here. And then we have to give it a value. So there's a couple different options here. We can actually specify a value at 10 degrees Celsius and another one at 20 degrees Celsius, and it will calculate the Arrhenius coefficient for us so that in the future that coefficient can be adjusted for temperature. I'm just going to do it the straightforward way here. I'm going to give this a value, give it a small value, say 0.5 or 0.05, sorry. And I'm going to actually enter that Arrhenius Arrhenius coefficient directly. And I have to specify the unit. Since this is a first order rate coefficient, that has to have units of 1 over day. Okay, so that's it for that model. And I'm just going to go back and do another validation check. And here, success, ASM1 is valid. So that looks good. Now, valid in the sense that mathematically it all makes sense. Whether it's actually a good model or not is of course, an issue of how it's calibrated and so on. But at least we can say from the point of view of what we need to make this run, everything that we need is there. So now we can go up here to the Generate Model button, and we do that. And we get this little window that allows us to, first of all, specify where we need those files to be written. And I'm working from the CN library, so I'm going to send it over to that folder. And I also specify which unit processes that I want to write this model for. So you can click them all if you feel like it. I'm only going to be doing just the CSTR today, just for today's example. And then we click Generate Model, and then it's done. It basically, all it does is it writes out a series of files, and I can show you those sitting here. And, oh, we actually wanted to... actually, I want to save this to a new name so that we can make it something unique that you can see. So let's save that under, we'll call it My ASM1. There we go. Now let's generate that again. There we go. And let's see here. Yep, okay, so we can see those My ASM1 variables. These are the files in the GPSX library. They have been created. Okay, so now what's left to do at this point is to close Model Developer. We have to restart GPSX in this particular case because all of the model files that you generate are usually read into GPSX only at the very beginning. So let's do that. So I restarted GPSX, and if I now draw out a little simple activated sludge plant, and here's my completely mixed reactor. I go there, and I connect all these together like this. We can now see when I right-click on this object that we now have a new model available. Previously, it would only been ASM1, ASM3, Mantis. Now here's my ASM1 model that I just created. So I'm going to select that. And if I go to the kinetic menu, the kinetic menu of the input parameters, we can see this new degradation of inerts constant that I just created when I was entering all that information into Model Developer. Here's the default unit that I typed and so on. That's all available, and that's going to be part of this new model now. So let's pop over to the simulation mode. So that's all compiled and ready to go. So if I hit start, it actually converges the model to an answer here under all these default settings. And we can see here that this model's obviously here. Let's actually click on that completely mixed tank. We can see here that we have a mixed liquor of 3,600. That's actually a little less than what I know the default to be, which is about 3,900. And that makes sense because of course now we're degrading a little bit of those solids that would have otherwise accumulated in the system. There's a couple of interesting things that we can do here now too, because that new rate that we were creating, the one that's doing the degradation, is now available for us to actually plot on a graph. We can, for example, go to the output variables menu, and we can go up to the My ASM1 rates menu, and we can open that up, and we can take a look at the growth rates, the death rates, and so on. And here's our new one, degradation of inert COD rate, and we've got a little over 40 milligrams per liter of COD per day being degraded in this particular tank. So you can multiply by the volume of the tank to actually get a mass of degraded inert solids per day under this particular system. So I realize I've gone through that example very quickly, but that's sort of the idea behind model developers, to allow you to come in to create some new parts of that biological model that wouldn't be there otherwise, and then actually add new equations right into GPSX and add new items onto the GPSX menu using our tool. Okay, so I'm going to go back to my slides. I realize I'm running a little bit long here, so thanks for hanging with me. A couple other things I want to quickly mention are that you can take advantage of a number of additional user-defined state variables in the GPSX libraries that have custom components. So here's a couple that are listed here. I was just working in the carbon-nitrogen library, but we have another one called carbon-nitrogen and custom components, the CN-IP library, that allows you to take advantage of 30 new state variables that are otherwise blank. They don't have any name and they don't actually do anything. They don't interact with the models, but they're there in case you want to use them in the future. So these are concentrations of various other components that you could do. So you can actually go in and modify our GPSX menus to actually name these and give these some meaning. You could, for example, I'm going to show you an example here in a moment where we're going to pretend that this SZA state variable, that's the fixed name that we've given to this particular state variable. We're going to say that's some sort of toxic component coming into the plant, and here we're going to show in the GPSX menu that this is operating at a certain number of milligrams per liter, and it can interact with the biology that's going on. So I'm going to quickly demonstrate that, but I'm not going to go through all the processes because that would take a bit too long. So what I'm going to do is just, I've put together, oops, I got to close this first. And I'm going to go to Model Developer here, and I'm going to show you the model that I already modified. So if I go to the CN-IP library, now we're going to take advantage of one of these extra state variables here, SZA, for our toxics component. And I actually made another model called Inhib ASM1. This is the ASM1 model, but in this case, I've left the matrix the same, but I've changed the model kinetics. In this particular case, I created a new term that is an inhibition term, and I've added it to all three of the growth rates that are up here at the top. The aerobic growth, anoxic growth of heterotrophs, and also the aerobic growth of the autotrophs. They now have this new term multiplied on the end here. That is actually defined over here, this inhibition term for that toxic component. And I used a simple, Monod type inhibition term here. There are many other types of equations that could be appropriately used here. Some of them that are probably more accurate than this, but just for simplicity's sake, I've used this one, which will inhibit the growth. This term will go to 0 when in the presence of SZA at high concentrations. And what that's going to do, of course, to this equation is we're multiplying by this term on the end. When that term goes to 0, we're going to be shutting off the growth. That's how you model toxic inhibition. Okay, so I've already generated that, and I've already made a nice little layout that sort of demonstrates that nicely. And what I'm going to do is run a dynamic simulation this time. So here's the toxic compound, and what I'm going to do is this little slider up here controls the amount of that compound coming into the plant. So what I'm going to do is I'm going to run that, and while it's running, I'm going to just ramp up that concentration and then move it around a bit and then ramp it back down again. Okay, so we can see that within the plant, we actually had this thing get up to a concentration of 68 milligrams per liter, this hypothetical toxic thing, and then go back down to 0 again. So now let's look at how the effluent was affected by this. And we can see here that while that toxic substance was present, the growth was inhibited. This is the effluent quality. We had pretty good stuff, effluent quality here, everything down below 15 milligrams per liter, until I ramped up that toxic compound concentration, and then we lost our BOD and we lost our nitrification and so on. And then when I got rid of it, eventually, it probably took several days, but eventually that all came back to life again, and we grew back our biomass populations and were able to move on. So this is how you can modify the existing biological equations to add in new things and see how that affects. In this particular case, it's an interesting one because this is a dynamic effect too. Okay, back to the slides to wind things up. Final thoughts. Model Developer is that tool that allows you to modify the biological part of the models in GPSX. You can add new processes, you can add new state variables, and it's one of our most advanced customization tools. It is in fact the tool that we use to build GPSX with. But it's very powerful, and we have a number of people, particularly research institutions, using it to be able to create new models, to be able to advance and develop the state of the knowledge in our industry. And we do have some consultants who use it to do things like that demonstration I just gave you now. I helped one of our clients not too long ago with a modification where they had very high saltwater content coming into their plant, and we used one of those extra state variables to sort of show some inhibition when the salt concentration was really high.